All right, so today's notes, we're going to cover section 2.5, which is solving compound inequalities. And what I think is really important to start with compound inequalities is just like a compound word, we associate two things at once, like a compound word like school bus is two words put together. So a compound inequality is an inequality that makes two comparisons at once. And there's two types of compound inequalities that we'll have in our work today. We'll have what's called an and compound inequality, and then we'll have an or compound inequality. So you can see that the words and or mean something specific. In math, the word and means both things are true. The or means one or the other is true. So for instance, we can look at this first example. This first inequality are the x's that are greater than or equal to 2. So we highlighted those. The second inequality is showing us all of the x's that are less than just less than 5. So if I thought about writing this as a compound inequality, which we did here, if I'm comparing both of them, so I just put the word and in between them, where are they both true? So where did I shade both dark blue and purple? Well, that's what we have right here on that last inequality. So this is where both are true. So it brings up a good point. And inequalities are always written as a single compound. And more specifically, what we see, that formula is a number, some sort of symbol, and the x's are in the middle. So that's our overall general form, and I'm just putting in a number to indicate that these are just numbers. So we have x's in the middle, and the numbers are on the outside. So in other words, our x's are inside those numbers. With an or inequality, just one or the other is true. So this first inequality is all the y's that are -2 or less. So that's these numbers. The next inequality is all the y's that are bigger than 1. So that's where we have this inequality. Now our final solution uses both of them. So an or inequality is always written using the word or, which we can see here. If I'm comparing these two inequalities at once, I'd put the word or in between them, and their final answer is written as two inequalities separated by the word or. We can make some other things, some other generalizations, like when they're both true, the and inequalities, we shade in between. For the or inequalities, we can see there's two shaded regions. So that's our beginning of trying to understand and versus or in math. So let's go look at something a little more specific. We need to write an inequality that describes the sentence and then graph each of them. So a number C is less than 5. So let's write that. So C is less than 5, and I see the word and C is greater than or equal to -2. So if I think about that on a number line, I want to see where are these both true. So I'd plot -2 and I'd plot 5. So let's graph this one first. All the C values that are less than 5 are right here. So I'm just shading the entire number line. I'd move over to my next inequality. C is greater than or equal to -2. I would graph that, so a closed circle at -2. And then I would shade this way. So I'm asking myself, where does my shading overlap? Where are they both true? So I shaded purple and orange right here. So my final graph, my inequality, would be -2. Now that is shaded both purple and orange, so we want to include that. But 5 is only shaded in purple. I put an open circle for the orange, so I'm going to keep an open circle there. And our final inequality, all of our C values are less than 5, and they're also greater than or equal to -2. So this is our final answer. So we're making sure to note things like a single inequality for and, and then we notice that we shade in the middle. The next example is an or. So what we should see is that or should always be written as two separate inequalities, and the graph should be going away from each other. So our number t is less than -1, or that number t is greater than or equal to 4. So this is already written as two inequalities, so we can write that for our final answer because or graphs are never combined. So I'm going to put an open circle at -1, and I want to shade all the t's that are less than that. put a closed circle at 4, and I want all the t's that are bigger than that. So this would be our final answer. And again, we're checking things like always written with or, and then the shading, there's 2 shaded areas. Let's do the last one real quick. A number A is fewer than -6, so A is less than -6, or it's not, so it's no less than -3. So in other words, it is no less than -3, so it's got to be bigger than -3. And no less than would also include the equal to. So this looks like an or, so I'd plot -6 and -3. Want all the A's that are less than -6, and all the A's that are -3 or bigger. So our final answer, again, we write our or inequality using the word or, and that's our final answer there. The next skill is actually solving compound inequalities. There's 2 types, solving with and. We can see that ands are always written as a single inequality, kind of like we did for our answer up here using and. Our final answer was a single inequality. And then there's some examples that use or, and we can see that ors are written with 2 inequalities using the word or. So it's really important when we're doing the ands just to make sure that we see that an and inequality now has quote unquote 3 sides to deal with. So I like to put in my little term separator, or my side separators here, because if we're trying to solve a compound inequality, we're trying to get the variable alone. So like on this example, here's our variable. I do not want a +1. So to undo a +1, I would -1. But we have to remember to do it to all, what I'm just going to put in parentheses or quotes as sides. So if I did it to the middle, I'd have to do it to the left, and I'd have to do it to the right. So -3 minus 1 is -4, and then this is x, and then this is 4. So this can be our final answer because it's an and inequality that was written as 1. So when we go to graph it, we know that our x's are going to be shaded in between -4 and 4. Looking at the next one, again, I want to get w alone. So I'm going to set up my separators so I know what I do to the middle, I have to do to all the other sides. So to undo a -4, we'd add 4 to all sides. -7 plus 4 is -3. Those canceled, and we have 6. And as we learned in other units, when I divide by a negative, we need to flip the signs. So on this side, divided by a negative, so I'd flip that sign. And then on this side, I also have to divide by a negative, so I'd want to flip that sign. Now, when we look at our final answer here, it is written as 1 inequality, but we want it to be in numerical order. So I need to rewrite my inequality. -2 is the smallest number, and 1 is the biggest, and w is in between. But we can go back to our 2 comparisons. In this comparison between 1 and w, the sign was eating the 1. So here, if I compare 1 and w, the sign should be opening towards the 1. As I can see above now, when I'm comparing w and -2, this symbol is opening towards the w. So here, when I'm comparing w and -2, that symbol should open up towards the w. So we can see that our final answer here follows the rules of ands. It's written as 1 single inequality with the variable in the middle in numerical order. So on our graph, we can clearly see that the numbers that we want to shade are going to be between -2 and 1. So a closed circle at -2 because of the equal, open circle at 1, and those are the numbers that fit in between them. When it comes to an or, ors can never be combined. So I put a big black line down the middle to remind myself that we just solve separately because we can never combine them. So I'm just going to do one at a time. So I do this one. So I'd subtract 6 from both sides because I'm trying to get this x by itself. And I would divide by 2. So I have x is less than -4. An or inequality always needs the word or. So I'm just going to go do this other side then. So I'd add 5. So I have 4x is greater than 8. Divide by 4. So we get x is greater than 2. And that can be our final answer. It's written in numerical order, and or inequalities are never combined. So when we graph it, we should see that these graphs go away from each other. In other words, there's 2 shaded regions. So if I graph this side, all the x's that are less than -4, put an open circle, and we'd want to shade less than that. When I graph the other side, I put an open circle at 2, and I want all the x's that are bigger than 2. So numbers like 3, 4, 5, and 6. So we can see again that our graph does match what we said before for OR inequalities. They should go away from each other, 2 shaded regions. So another OR example, I separate them, I just do one at a time. So we'll focus on the one here. So to get p alone, we'll subtract 1 from both sides. So we have 2p is less than -8, divide by 2. So p is less than -4. Or, because remember, OR inequalities always need the word OR. So here's my p-value. So put in my sides, I'm going to subtract 3. So those undo each other. We didn't undo the negatives, so that's still there. Now in this case, I'm about to divide by a negative. So if I divide by a negative, I have to flip the inequality symbol. And this would be our final answer. OR inequalities should not be combined, so we leave it with the word OR. And when we go graph it, we should have a graph that's shaded twice in separate directions. So here, -4 is the biggest, so I'm going to shade stuff that's smaller. And then here, p is greater than or equal to 2, so at 2, I'm going to put a closed circle, and then shade the numbers that are greater than that. So again, just kind of summarizing this page, what's really important is to make sure that when you're solving and inequalities, that you do it to all the sides. And then making sure that you write your answers in the right way, whether it be an and inequality or whether it be an or inequality. And we just summarize saying and inequalities are in numerical order, and they are not combined, or excuse me, they are combined into a single inequality. The or inequalities are not combined, and we see their graphs go away from each other.